All right, well, thanks everyone for coming. I think a lot of people are new to machine learning. Machine learning itself is kind of new, you could say. It's in some sense really old because it comes out of multivariate statistics, hundreds of years old. But its own little flavor, you could say, is kind of new-ish. But there's a lot of confusion even within the field of machine learning. This particular question is kind of a confusing one, and gets extremely technical. Gets right at the heart, of course, of machine learning theory and practice. So everything I'm saying today, you can believe, is a very, very cartoonized version of many, many technical questions and problems that there are actually hundreds of papers that directly deal with this and so on. Okay, so I'm going to, and yet, as a person trying to do machine learning, you don't have time to read hundreds or thousands of research papers. So I'm going to try to give you kind of best back-of-the-envelope advice, kind of, from my perspective. As Monica said, I've been doing this for 20 years now, almost exactly. I don't know how many data analysis problems I've worked on, at least 100. So this is based on lots of practical experience. Before grad school, I was in the trenches at NASA as what is now called a data scientist, writing code and mucking with data and so on. So I think I view it from both sides, the theoretical and academic side as well as the practical side, and have had the opportunity, in particular through Skytree, to have worked on a lot of really big, important problems. So that I'm thankful for. And so anyway, so that's where this is coming from. But we preface it by saying this is highly cartoonized, and it also tends to for certain people, because it's at the heart of machine learning itself, it gets people emotional sometimes, and they get excited. Don't get excited. This is, if you do get excited about something, positive or negative, talk to me. I'll tell you some of the kinds of conceptual camps that tend to get very emotional about these issues. Okay. So this is the only advertising slide about Skytree, I promise. So anyway, this is just some background on what we are. Machine learning for the enterprise, the highest performance machine learning. We think. We are right out of the halls of academia, kind of, but also extremely practical and enterprise focused. Okay, so machine learning, brief history. Like I said, before this, in the timeline, you could say is multivariate statistics, going all the way back. AI, pattern recognition, coming out of the double E world. In the 80s, everything was neural nets. You couldn't say machine learning, kind of, without really saying neural network. Data mining, kind of. Mid-90s, that roughly, arguably, was the turning point, the modernization of machine learning, the computer science kind of take on machine learning, which now more or less encapsulates all of those other names. Okay, we can argue about all of this, but roughly there's a convergence in techniques and viewpoints all around what I would call modern machine learning, which is directly grounded in statistics. It is nothing else but statistics, and it turns out advanced computation needed to do things tractably. Okay, and now, because of a few pivotal, I think at least a few pivotal points, become, everyone wants to do machine learning. The Netflix prize, I think, kind of was one turning point where people realized, this whole recommended personalization thing kind of makes money. It's connected to money, and it's important. And Google AdWords, well, you could argue there is no search without machine learning, because machine learning is what lets you do the targeted ads. So no money, no search. So we're here. Everybody wants to know about machine learning now, but still a lot of confusion, and it's not clear exactly where to look. Okay, you kind of know this. This is just saying machine learning essentially is everywhere now, at least in pockets, at least, or in many cases, the leader in some industry is using machine learning, whether they're saying it or not, and so it's just a matter of time before everyone will need to do machine learning. Okay, so roughly, how do you do machine learning? Well, there are 7 easy steps. Highlighted in light blue, that's the one I'm going to focus on. There are other steps, they're all important. I'm going to have to touch on at least 2 other ones in the dark blue, okay? But the steps are, number 1, always understand your goals. That's not necessarily easy. Obtain and prepare your data, of course, not necessarily easy. You obtain and prepare data that in such a way that it meets your goals. You got to understand what you actually have, also not easy. Choose which machine learning task, usually pretty easy, but there are still many ways to achieve the same thing. Sometimes you can achieve the same thing with multiple different machine learning tasks, formulating them differently. And then finally, once you've chosen a machine learning task, by that, for example, classification, then there are a whole bunch of classifiers. Which classifier should be the one? Okay, then you run that, you try it, but trying it thoroughly is important. Otherwise, as in any kind of scientific experiment, and you should be thinking scientifically, not emotionally, how well did it do? Well, you have to have executed that experiment thoroughly and well, or else you don't really know. Understand the results, of course, then repeat. Repeat may jump to any of the other steps, sometimes all the way back to number 1. Rethink your goals and so on, okay? And then when you're done, deploy it. So we're going to focus on number 5. Many other interesting things to say about all the other steps, but we won't do that today. Okay, so I just want to know, what's the best method? What's so hard about that? Well, one is sheer complexity. There are thousands of machine learning methods, actually. In fact, there are probably thousands that appear every year. There are a lot more researchers than you're probably aware of on the planet Earth. There are just hundreds and hundreds of papers being generated. Most of it is crap. But you don't know. It's hard to tell what's crap and what's not. Okay? Even we don't know as researchers until a while later sometimes. Okay? Well, surely somebody smart, a leader of a field or somebody, has written a textbook and kind of tried to summarize it. Yeah, a little bit, but textbooks, for one thing, are for researchers, and so the problems themselves are couched one level down, not at the practical level. Okay? And most professors are not practitioners, and so they don't even care about the practical problem. Okay? There are now, have been for a while, but there are especially now practical guides written and out there, and there are some good ones, but there are also some inexpert ones, and so whatever claims are made may or may not be true. In any case, often because they're practical guides, they're incomplete because they need to be short and pithy. There are, and this is a dastardly one, there are hidden subjective biases too. And I'm going to try to expose at least a couple of them, which have nothing to do with reality. They're just taste. Okay? Taste is loosely based on reality, but extremely loosely. So, and then you might go, well, surely, because this is such a central topic, somebody must have done a comparison. Yes, It turns out that, especially around the 90s and so on, there was a lot of this kind of activity. And there's a comparison at the end of half of all machine learning papers, which is my new machine learning method that I'm trying to push. That's what my paper is about. I'm hoping that it'll get accepted, and so I do a little comparison at the end of the paper with other methods. But everyone knows it's usually a cheat. There are usually many, many cheats in there because you're trying to make your method look good. Okay, because that's the currency of academia's papers. If it doesn't look good, it won't get published, and I won't have a long list of papers. So, anyway, even if I wanted to do a fair comparison, it turns out it's difficult. There are things you have to hold. If you're a real scientist, you hold things constant, everything constant, except the thing you're trying to get at, which is somehow the fundamental statistical performance of your method. But there are other things, like, and maybe you're worried about computational performance too, but things are written in different codes, they're written by different authors. If you're trying to compare runtimes, they have different inner loop functions that they use. One might be 10 times more efficiently coded than another, and so on. Okay, so you need some kind of big standard software base that's uniform in expertise over all of the methods, and so on. So you can imagine it's not actually easy. So, and it's a massive effort, and nobody to date has done what anyone would accept as a very thorough comparison across all machine learning methods. Just nowhere near possible. Even though there are some movements, there have been some attempts. Okay, and competitions. What about competitions? That's a new thing. Yeah, interesting, but definitely not thorough. Depends on who enters. Not all of machine learning is represented, certainly, and certainly not fair. Why? Because it's for one problem, for one thing, and anyway, if the person representing this method, who happened to use this method, is smarter than the person representing this method, it's not a fair comparison. And if they are more motivated, this person is more motivated than this one and puts in a lot more energy and has a bigger team, they're going to win. So I'll explain a little bit more about why that is. Okay, so that's why you basically can't find out by looking this up anywhere. So what is machine learning? Well, let's break it down into 7 common machine learning tasks. And, again, this is really for people who are new to machine learning. I know some of you out there are experts. You may or may not find anything valuable in this talk, but hopefully, if you're new, you may. So here are the tasks. So one, you could say, for kind of modern data analysis is multivariate querying, not just SQL querying, but a query like find the nearest neighbor for this point, this data point. Find the k nearest neighbors. That's an overall measure of similarity over all of the columns, not just 1 or 2 columns. Number 2, and I'm only going to talk about 2 through 6 in this because the 7th one is a little esoteric and the first one doesn't really have a lot of conceptual options. Number 2 might sound funny, but it's really just like the equivalent, like a histogram, generalization of a histogram. How common is each type of object? Okay, what is the density or distribution of the points? Why would you use that? Well, to find outliers, for example, and so on, or just to understand how your data are. So classification, this is probably the most common thing that's done. Why? Because it's very natural. You're trying to predict. Here's a little picture of a data set. Think of a data set as a table. It isn't always, but it always is conceptually. So from the first 4 columns, the variables represented by the first 4 columns predict the 5th column. If the 5th column is symbolic, A or B type variable, cat or dog, then that's called classification. If it's a number, like predict someone's income, continuous value, that's called regression. Dimension reduction is, there are 5 columns, but or 4, I want to understand, I want to be able to plot it, let's say, so I need to squeeze it down to 2, because I can only plot in 2 or maybe 3. So let's somehow preserve the information in the data set, but squeeze down the number of columns. Clustering is to find groups in the rows. So if it's a customer database, I'll automatically figure out there are 3 types of customers, the kind who buys a lot and is very young, and so on. And then the 7th one's a little esoteric. Scientists do this. It's very critical in science, but and eventually I predict it will be more common in industry. This is the kind of thing like I have 2 data sets. Let's say customers in the fall and customers in the spring. Do they look the same? Do these distributions look the same? Okay, and if not, what's different about them? Okay, or matching 2 data sets. These are potentially the same customers, or some subset of them is the same. Match them. Okay. All right, so that's machine learning defined by enumeration. Okay, but then for each task that you're trying to do, you have multiple methods, unfortunately. So if you're, and then it gets confusing, and then you have a million terms. And I'll go through these, but and I'm not going to mention all of them, of course. There are thousands of them. I've just picked some common ones / some ones that I think are interesting that maybe more people should use if they knew about them, because they have interesting, they're interesting extremes along certain axes of performance. Okay, so, but, you should at least know when you hear about a machine learning method, what is the task that's for? Once you've done that, you've gone a fair ways. You at least know what it is, what it does. Okay, but like I said, there's an entire zoo of them that we don't have time to discuss. Okay, and in fact, there are much more powerful methods in the research literature. At any time, the research literature has stuff that won't appear in textbooks for another 5 or 10 years sometimes. Okay, but so everything on this list is already old, and yet very little of it is actually used in industry. Okay, so what do we mean by best? So there isn't just one axis of bestness. So at least 4 that are kind of important, and there are, of course, more, arguably, but at least one, arguably the most important one, is accuracy. All of these tasks can be phrased as some kind of prediction task, even though it may not seem like it. Okay, but it can be cast formally, mathematically, as a prediction task. That is one way to define machine learning. Okay, so accuracy, well, if I predict better, this model predicts the future better than this data set or this model, then that's what we mean. And then, in reality, the speed is important now that we're talking about big data. Okay, so speed is incredibly important because it's fundamentally tied to accuracy. And there are 2 types of speed, you could say. It takes a certain amount of time to take in data and train the model. And then once you have a model, you have queries to the model, things that you're trying to make predictions on, and that we call that testing. And at test time or prediction time or production time or scoring time, these are all synonyms, then there's the time it takes to make a prediction, okay, for the model to make a new prediction. They're both important in different contexts. And related to speed, of course, is scalability. So scalability meaning, can I handle more data? And if I want to handle more data, well, I only have a certain finite amount of time as a data analyst or data scientist. So in the same amount of time, whatever my patience threshold is, or however much time the boss has given my group to make the model, 3 months or whatever, how much data can I run on, and how many different model parameters can I run on? Because I set some parameters usually, some knobs on a method. Most methods have knobs, not all of them. And then I try it, and then I twist the knobs again, and I try it. And I keep doing that until I get the accuracy up. Okay, so the faster I can do that, the more knob settings I can try, and the more different methods I can try, different machine learning methods. Okay, so that's why speed is fundamentally tied to accuracy. Okay, then, very important, not always, but in some cases critically important, I want to understand why it made that prediction. Okay, it says your credit card, you were denied a credit card. Why? So that could be very important. Some methods are interpretable, some are not, basically. And 4 is simplicity, which refers both to how easy it is to code it, kind of, but what I mainly mean is fiddliness. Some methods are very fiddly. They have a lot of knobs, and it's actually sometimes okay if you have a knob, but you know exactly how to tune it. You can make an automated procedure for tuning it. But for some methods, it's difficult because of the nature of the optimization problem. You have to just try a bunch of stuff, and you have to fiddle a lot. Use intuition and make plots and so on. Okay, so how automated or non-automated is it? Okay, now, these are all different things. There are fundamental trade-offs. Sometimes you can get all of them, very rarely. Nothing comes for free. So, generally speaking, accuracy trades off with speed. Life is never perfect. You want high accuracy? Usually that you pay, almost always, you pay in computation. No getting around it generally. Okay? Accuracy versus interpretability. Generally, the more accurate it is, the less interpretable it is. Okay? The highly interpretable methods, not as accurate. And accuracy trades off with simplicity. So accuracy is usually what you care about. It trades off with all of the other ones. Okay, unfortunately. So I'm just going to tell you 2 or 3 concepts before we get into my cartoonized, I'm going to give you a table listing the pros and cons, kind of my little qualitative cartoon rating of a bunch of common methods. Okay, but before we do that, a few concepts. So, parametric versus nonparametric. What does that mean? It's a confusing terminology, but generally speaking, parametric means there's a finite number of parameters to the model that doesn't depend on the number. It's not tied to the number of objects or rows. That's all. It just has, 10 parameters. And then, but there may be 100,000 rows, but there are always 10 parameters. You might increase it to 500,000 rows, but there's still 10 parameters. We call that parametric. Okay? It usually, the reason you can decouple the two is that you're making a strong assumption about the underlying functional form, the shape of the function underlying the data. Okay, and because of that, it's an assumption, a strong assumption. Your data usually do not meet that assumption. And therefore, it's not an accurate method in general. Okay? But you can always get lucky. You can always assume a linear underlying form, and then it is linear. Great. These are general statements about what typically happens over, you could say, over the distribution of all data sets, although there's no such thing. That's what my statements are sort of trying to capture. But if you get lucky, so none of my statements are ever strictly always true. In fact, there's a theorem that says that. Okay, so this is rough. Please don't get all fussy about it. But generally speaking, when you assume a linear underlying form, it's generally not true. Okay, you're lucky if it's true. But because it has a simple functional form generally, it is a simpler model. In fiddliness, it is more interpretable, but less accurate. Okay, so roughly those trade-offs can kind of boil down often to which type of method is it? Is it a parametric method or is it a non-parametric method? If it's non-parametric, then the number of parameters in some formal sense is proportional to the number of rows, which sounds horrible. People were very afraid of such methods. Although in practice they're very simple. There's some very simple instantiations of such methods, like nearest neighbor, for example. But formally, the number of parameters grows with the number of data points. What that means is you can intuit that means that you can fit arbitrary functional shapes. You have so many parameters that you can fit anything, basically. Okay? Non-parametricness there is a formal statement of what it means to be able to fit any functional form. What it really means is under weak assumptions about the functional class underneath your data. Okay, but anyway, because you can fit any shape, it's generally more accurate. Okay, you can't beat a non-parametric method generally, unless you're extremely lucky and you got exactly the right functional form in your parametric model. Okay, but more complex, as you can imagine, and thus less interpretable. Sometimes it's a big mishmash of tiny little functions glued on top of each other and stuff like that, and a lot slower, a lot slower. Okay, so that's more, and I've given examples here. Or I've divided up the methods that I listed into these two types, parametric and non-parametric. The line can get fuzzy for certain methods, okay? But more or less, we can prove whether something is non-parametric or not. Okay? That's going to be important. So, like I said, theory tells us, in fact, that there is no best. And it kind of tells us that all my charts are cartoons. Because, like I said, you can always get lucky. It just depends on your data set. Okay? That's what the no free lunch theorem says. This was in the 90s. It was shown basically by a simple argument that whatever classifier, let's say you have a classifier that you think is the best, I can always come with a data set that's really bad for your classifier. Okay? Inductive bias is this concept also from that period, which says, in fact, there's a kind of function that's best, in a way, for each machine learning method. There's like that it's kind of biased toward. It kind of likes to see that kind of function. It does better for those functions. Okay? One more thing, or a couple more things, before I show you the comparison. So this is the subjective one, the non-scientific one, in my opinion, that influences some people to make strong statements in favor of certain methods over others. So you might read entire diatribes about certain methods, trying to poo-poo other methods. That's usually because of one of these two types of things. Very old and fiery, still goes on, fiery debate in taste is between the so-called frequentist methods and the Bayesian methods. In reality, anybody who's been doing this stuff as long as I have, for example, doesn't really care anymore. I don't care. But there are certain people who care deeply and will fight about it and so on. It's mainly philosophical. More or less, it's about whether you believe that parameters are objective kind of features of the universe, or do you believe that they're subjective? Okay, it doesn't matter. Now, what matters, in my opinion, I've done papers on both. Nobody cares. So, but the full Bayesian, if you go all the way, I will say there is one practical thing to keep in mind. If you insist on the Bayesian thing, which is beautiful in its own way. There's a reason people get hot and bothered about it. It is kind of elegant. But if you take it all the way to its proposed extreme, then it leads to intractable computations. Can't do it. Okay, so you never want to be a full Bayesian, in my opinion, if you're trying to do practical stuff. Okay, so a lot of work in Bayesian inferences to make this stuff kind of tractable. Okay, then you may have heard about something called deep learning. It's kind of it's a resurgence actually of the stuff from the 80s, neural networks, which were never a bad idea. They kind of were surpassed by other methods practically. But and they kind of resurged in the form of deep learning, and people have actually shown some good results. So, but the whole neural networks / deep learning have this biological motivation. They were meant as originally as models of the brain, the actual human brain. Okay, so that's super interesting, and has a whole scientific side to it, as opposed to practical side. But people get really up in arms in both directions about it. Deep learning sucks, neural networks suck, or the other way. No, it's the only way to go. Okay, so keep that in mind when you read stuff. Now, there's a whole bunch of other stuff, each of which could be a whole talk on its own, which is important for your problem. Maybe you don't care what works on average over all problems in some sense. You actually care what's going to work best on your problem right now you need to solve in 2 weeks. Well, there's sensitivity to outliers. So different methods are more or less sensitive to outliers. If you have outliers, that could change your entire selection. If you have missing values, some of the methods easily handle missing values. Missing values means in my data table, one cell may have no entry. Like for this customer, there's no zip code. It was never entered. It's missing. It's a question mark. That totally destroys some machine learning methods, but for others it doesn't. It's okay. Okay. In some cases, your objects of interest are not fixed length rows with a D or whatever, a fixed number of slots. They're actually funny things like molecules or parse trees of documents or some XML objects or something. There you can do machine learning on such funky non-vector things with some methods, but not others. Okay. Sometimes in a classification problem, let's say my classification problem is I have customers who bought in the past my product when I advertised it to them, and customers who didn't buy. Well, the ones who didn't buy, unfortunately, is 10,000 times bigger than the size of the data set for people who bought. Okay, but I want to do a classifier, but I have this 10,000 to 1 imbalance. Well, some methods can handle that well, some methods can't. Most of them can't, actually. Okay, high dimensions means I have a huge number of columns, maybe, like in internet advertising. I may have millions of columns because the columns correspond to different keywords that they might have. It's a 1 or 0 depending on which keyword was entered. Some methods very good in high dimensions, some not at all. Okay, and then some can be extended to so-called dependent data, where the data are a time series rather than, in other words, there's an ordering on the objects. For example, stock market prices. You can't just shuffle them. Today's price came after yesterday's price. So some methods can be extended that way and some can't. Okay? So lots and lots and lots to say there, but let me jump to my little cartoon. So density estimation. So your common methods, mixture of Gaussians, and kernel density estimation are very well known. I throw in, just for fun, another one, which actually I introduced. Why? Because it's a natural extension of the decision tree, except for density estimation. So anyway, I think it's fun, but because it introduces some extremes. So I put it in bold, extremes. So, and of course things aren't always clear, so I put a slash sometimes. Low to medium for simplicity of mixture of Gaussians, because you have to fiddle with lots of parameters. But it can be extremely fiddly, so it can be low in simplicity mixture of Gaussian. But otherwise, kind of okay. Mediums, highs. Density estimation tree can be super slow at times. So I put a low there. But it can be extremely fast at test time. I put very high. Very interpretable because it's a tree of rules, just like a decision tree, and no parameters, automatic, simple. Okay, kernel density estimation, also extremes, and you see here already, this is a non-parametric one. The second two rows are non-parametric, and they can achieve higher accuracies. Mixture of Gaussians is actually half parametric, half non-parametric, you could say. But here you see the extreme of a fully non-parametric method, kernel density estimation. That's how you achieve the highest accuracies. You're trying to estimate a density. That is the gold standard. Very high. Speed, low. Okay? Two extremes, both at test time and train time. Okay? Classification, 2 slides for classification because there are so many methods for classification, all based on different ideas. Some of you may have heard of logistic regression, parametric, low accuracy in general, very high speed, test time. Okay, so also extremely simple, no knobs to tune, automatic. Decision tree, actually sort of okay on accuracy, medium, kind of okay on speed, but super fast at test time. You could argue the most interpretable. Very high on interpretability. You can read it off as rules. Okay, the rules say, well, why did you deny me my credit card? Because people who are less than 20 years old and make less than 15K in income tend to default. You can read it off as a rule. Okay. Okay, simplicity, no parameters to tune, does it automatically, very high. Nearest neighbor, now we start into the methods that are fully non-parametric. Decision tree is actually non-parametric, but with a simple aspect to it. Now we get into methods that really can fit any function pretty well. Okay, all these, this whole set of next methods, these 2 on this slide, and then the next 4 or so on the next slide, all can achieve very high accuracy. In fact, the highest. So in a competition, in other words, if I take nearest neighbor and he takes kernel discriminant analysis, we're going to get extremely close to each other. It just depends on who's worked harder. Okay, but very slow, generally. Okay, and then you see the same theme here. Neural networks support vector machines, and I list with commas the 2 types, linear and nonlinear support vector machines, or kernelized, random forest, and boosted trees. Okay, a lot of people really love random forests. They are a kind of a nice trade-off in some ways, you can see here, but not in true interpretable always. But they are among the set that can achieve the highest accuracies. Are you always going to win with a random forest? No. Sometimes yes, sometimes no. There are many non-parametric methods. It is decent, kind of speed-wise, in both cases, but other things are too, can be. Okay? Boosting, some people go nuts over boosting. Same thing, is in that kind of good set for high accuracy, but has other trade-offs. Okay, 2 more slides. Regression, this is predicting a number instead of a category. Linear regression, simple model, parametric, low accuracy, unless you're lucky. If you're lucky, it is aligned. So again, no strict statements, but super fast, kind of at test time, because it's a simple model, very interpretable. You can see the coefficients tell you which dimensions are important. Super simple, no parameters to tune. Okay, so there's no such thing as, certain methods are crap. No, they're all good for different things at different times. Lasso, kind of a modern variant of linear regression. And then the next 3 are non-parametric, okay? So this is how you get the very highest accuracies, but you see the last one, that is very hard to beat in accuracy, extremely accurate. Super slow. Actually, among all of these, that's the one I never figured out how to make really scalable. That is an open problem. Okay, last one, dimension reduction. The first three are linear models, parametric, simple, very fast at test time, kind of fast at train time, not the most accurate. The last one is a way to make these methods nonlinear or non-parametric, and that's going to be expensive but accurate, you could say. Okay? Computationally expensive. Can't interpret it very well. Not simple at all. Oh, one more, clustering. You've all heard of k-means, simple parametric clustering. Hierarchical and mean shift, you could say, are non-parametric. Not super provable, actually, but you could say intuitively non-parametric. Again, high accuracy, low speed. Okay, but clustering in general is always kind of interpretable, you could argue. Hierarchical clustering, no parameters, basically, very non-fiddly. The other one's kind of fiddly. Clustering is notoriously fiddly, actually. Okay, summary. Know the most common, here's my advice, basically. You should know the most common / most important machine learning tasks and methods. Decide what trade-offs you want to make or need to make. Understand at least parametric versus non-parametric. And understand the conceptual camp so that you know what the author is actually has in mind with his or her diatribe. And experience the pros and cons of each method yourself. Don't take my word for it. Try it on your data and see for yourself. That's the only way to really feel extreme slowness or high accuracy and things like that. Okay? All right. Thanks.
Okay, we have time for one question.
If we don't get to your question, just email us. I'll be around.
Hi, I was wondering what your thoughts on are on ensemble learning.
Yeah, ensembles. So I showed a couple of them. Random forests. More generally, bagging is the more general principle under random forests. Boosting and so on. So if you take ensembles to an extreme, the Netflix prize, for example, was famously won by not just an ensemble, but a heterogeneous ensemble. A whole bunch of different methods kind of glued together in an ensemble. That's how you get the highest accuracies, yes. But you pay in other ways. So, yeah.
Okay, let's thank Alice again, and we'll see you later at 4.